many of us expected this would be a mission of major discovery, but I think none of us really expected the degree of discovery, the degree of diversity which we found in the outer solar system.
We were lucky. We had the unique opportunity to explore planets that man had never been to before.
But Voyager didn't only carry sophisticated instrumentation, it carried the hearts and the minds of its creators and all of us who were privileged enough to see what it saw.
And it will be unique for a long time, because there isn't anything else out there to explore for which you can get as much return from a single system.
I think Voyager will be remembered as part of the few decades where the human race left its planet. And Voyager will be a main chapter in that book.
Voyager kind of opened up the outer planets to everybody, and I think they were vastly more interesting than we expected, up to and including maybe even especially Neptune.
You only explore the solar system for the first time once. And we did it.
The outer planets are giant planets. They're distinctly different than the smaller, rocky objects in the inner solar system, such as Earth, Mars, Venus, and Mercury. And Voyager was designed to open up to exploration these giant outer planets, which are spheres of rotating fluid and gas surrounded by 57 moons totally. Each planet has a unique ring system, and they have magnetic fields which are immense compared to the magnetic field of Earth. Voyager's job was to explore those worlds in the outer solar system.
Scientists at Cape Canaveral, Florida, sent another unmanned Voyager spacecraft on its way to Jupiter and Saturn today. It lifted off flawlessly at 8:56 a.m. and had none of the problems of the Voyager launch 2 weeks ago. This Voyager presumably will get to Jupiter in March of 1979.
Voyager 2 scared us. Voyager 2 had problems in separating from the solid rocket kick stage. The spacecraft today, you know, have a few problems, but most of these problems were problems we experienced early on. In other words, the Voyager 2 spacecraft has a failed receiver and a sick backup receiver. That's the most serious problem on board that spacecraft.
The way we communicate with the Voyager spacecraft is that we send commands to the spacecraft, a series of digital bits in computer language that go to the spacecraft, and it's the language that the spacecraft understands. These bits are transmitted from ground stations located around the Earth, what we call the Deep Space Network.
The 3 Deep Space Network stations are located in Goldstone, California, outside of Madrid, Spain, and outside of Canberra, Australia. As the Earth turns, we can maintain continuous communication with a point in space, the spacecraft.
In turn, there's kind of the reverse link coming back down. The information that the spacecraft gathers goes into a transmitter on the spacecraft. It's transmitted into those big ears on the ground of the Deep Space Network and transmitted back then on the ground to our control facility here in Pasadena. The transmitter on Voyager is like tens of watts. It's like 20 watts, less power than an average light bulb on your front porch might consume. On the other hand, when that signal is received on the Earth, it is literally a tiny, tiny fraction of a watt that is received. The amount of power received by the ground antennas is something like a billionth of the amount of power used by my digital watch.
Man has known about the planet Jupiter ever since he took a good look at the night sky. It's not what you'd call a near neighbor, though, being more than 400 million miles away. But after all these centuries, we're getting a closer look than we've ever had.
When Voyager got up close and we looked at the time-lapse movies of the atmosphere in motion, things were changing every day. Little storms would pop up out of nowhere and they'd get ripped apart, dispersed, all in a day or two. And that made the mystery of the Great Red Spot and those other large spots even deeper, because how could they last for so long in the midst of all that chaotic motion? It was a startling discovery.
As Voyager approached Jupiter, the first thing that it intercepted was what's called the bow shock. That's a shock where the supersonic solar wind becomes subsonic. And that shock, the solar wind velocity, which is 1,000,000 miles per hour, abruptly decreases to 250,000 miles per hour. That abrupt change in velocity causes the ionized gas to vibrate, and we can sense, we can hear the shock, and we can hear the vibrations associated with that shock as the spacecraft flew through the shock itself. We had expected that the magnetic field might extend something like 1,000,000 miles or so from the planet. In fact, it extends some 3 to 4 million miles from the planet. Now we understand, because Io is injecting into the magnetic field some 1 to 2 tons of material every second. And that material, as it spins with Jupiter, is centrifugally expanding Jupiter's magnetic field, inflating it to a much larger size than it would normally be.
We expected, quite frankly, the satellites of the outer solar system to be quite bland and geologically lifeless. As we flew closer, Io looked less and less like anything we'd ever seen. The impact craters turned into irregular dark patterns and the colored patches, red, yellows, painted on the surface. As a matter of fact, as we flew closer, we saw nothing at all that resembled an impact crater. Voyager 1 discovered 11 active volcanoes, and 9 of those were still active when Voyager 2 returned 4 months later.
I think the event in the mission which really altered our view and our expectation for the rest of the mission was the discovery of the volcanoes on Io. That was such a dramatic and unexpected thing to find that it really told us that we could no longer be complacent. We could no longer expect to understand or anticipate what we were really going to see.
Voyager 1 flew in close to Io for a close-up flyby of Io to give good return from Io, and made its close encounters with the Galilean satellites after the closest approach of Jupiter.
If we look at Callisto, it's one of the most heavily cratered objects in the solar system, virtually saturated with impact craters. When we looked at Ganymede, we find 2 kinds of terrains. One is a terrain that looks very much like Callisto, but in addition, Ganymede has a very complex intersecting network of faults in a younger terrain, which has evidently welled up from the interior and replaced this old cratered terrain that's so similar to Callisto. In the case of Europa, we see yet another style. We see gargantuan fault patterns in which this ocean has frozen repeatedly, broken open, and fluids float up to the surface, producing dark puddles of material within the faults. These are then broken again, so there's intersecting and cross-cutting networks. There were 2 small satellites discovered at Jupiter. One of them found orbiting just outside a very thin, tenuous ring of material that was discovered at Jupiter.
The imaging team members planned one single photo, an 11-minute exposure that would be taken as the spacecraft plunged through the equator plane of Jupiter. And it just so happened that there was a ring there. It's dusty, and there seems to be no indication of water or ice within the ring, so it's probably made out of rocky material.
An outer space spectacular that was the stuff of dreams only a generation ago began snapping into the sharp focus of reality today. After its billion-mile journey from Earth, the Voyager 1 spacecraft sent back pictures of man's closest look yet at the ringed planet Saturn. The closest encounter of spacecraft and planet occurs later tonight when Voyager sails just 77,000 miles from Saturn's yellow clouds. But already one scientist said, in the strange world of Saturn's rings, the bizarre has become commonplace.
The closer that Voyager got to Saturn, the more and more detail and structure Saturn's rings turned out to have. And this just was an enormous surprise to everybody. The rings were simultaneously breathtaking but completely baffling. And there was just far more structure than people had anticipated. Not only did we find many, many concentric features within the rings, but we found eccentric rings. We found that the F ring, which had been discovered by Pioneer, had braids in it and kinks and clumps, all these things no one had ever even dreamed about before Voyager got to Saturn. And then, of course, there were the spokes that Voyager discovered about a month or a month and a half before encounter. And these are these radial features in the B ring that come and go. They are seen orbiting around the rings, and no one had a clue, or at least not a reasonable clue in the beginning as to what caused these features or even what they were. That if you look at the rings of Saturn for a period of time and watch the spokes go around and round, and you examine the appearance of the spokes on the rings, that appearance changes, and it changes with a period that is equal to the period of the spin of Saturn's magnetic field.
Voyager found that Saturn's magnetic field, as Pioneer 11 had already told us, is weaker. That is, it's only about 1/20th the strength of Jupiter's magnetic field. That means its magnetic field doesn't extend as far from the planet, about 1 million miles from the planet. What Voyager discovered was how rapidly that magnetic field was rotating. The magnetic field at Jupiter rotates with a period just under 10 hours. At Saturn, it turns out, the magnetic field rotates with a period of about 10 hours and 40 minutes. So this was the first measure of the length of the day on Saturn.
Turns out, when we finally measured the magnetic field and the radio emissions that are tied to the magnetic field, that the inside of Saturn is moving quite slowly. Well, it's moving more slowly than most of the storms in the atmosphere. And the difference in those speeds translates to 500 meters per second for the winds, which is over 1,000 miles an hour. And that made Saturn a lot windier planet than Jupiter. And that was the big surprise for me when Voyager got there.
Voyager 1 approached Saturn in such a way that it flew past Titan before its closest approach to Saturn. That trajectory then, because of the tilt of the satellite system around Saturn, caused the spacecraft to fly low initially and then get deflected as it made its closest approach to Saturn, going through the ring plane up out of the plane of the ecliptic.
We knew that Titan had an atmosphere. We had no idea how deep it was or what it was made out of. And what Voyager found was a nitrogen atmosphere with traces of methane and other hydrocarbons. And it turned out to be quite a deep atmosphere.
We suspect there might be an ocean of a material called ethane. There could be all kinds of complicated hydrocarbons of different colors and different states, some ices, some fluids. There's all manner of hallucination about hydrocarbon goop that rains out of the atmosphere and falls on the surface. As a matter of fact, Titan remains one of the really exciting challenges for future exploration. In the case of Mimas, we see a crater on Mimas that's about 40% of its diameter. A little larger, and that would have been enough to shatter the object. And of course, we wouldn't see the crater then, because it would reassemble like a kind of a giant ball of sand. And in the case of Tethys, there's another very large crater, even larger than the one on Mimas. But in that case, notice the floor is now rounded out so that it is curved as the rest of the object's limb is. In the case of Dione, you'll notice that most of the surface is pretty bland. And only in this one region near the trailing hemisphere do we see a lot of detail on the surface. Here we see a lot of crisscrossing faults with wispy bright markings around them. Finally, we look at Enceladus. We're talking about very cold regions. And here we are with this little tiny object showing geologic activity of the scale that Enceladus does, in which the ancient crater terrain has been broken and has collapsed into the interior. Fluids have flowed out into those open gashes in the crust repeatedly.
Yes, affirmative. I can see a X-ray band shown.
Well, after we got Voyager 1 to Saturn, we went back to NASA and said, we have now satisfied all of the objectives for the MJS, for the Voyager mission. How about giving us money and giving us permission to target Voyager 2, to tweak its trajectory just a little bit so that we can go on to Uranus. Now, there was a penalty for this. The data that we got, the quality of the mission at Saturn was a little bit less if we targeted for Uranus than it would be if we optimized for Saturn. And we bared all those facts to NASA. We told them that it was maybe a 60–70% chance, but we thought it was worth it. And I guess we were pretty persuasive because they bought the idea. Soon after Voyager 2's closest approach to Saturn, in fact, while it was behind the planet, its scan platform got stuck. It had a mechanical failure, and we weren't able to aim the cameras and the other pointable instruments on the spacecraft at the targets. After several years, we concluded that, in fact, during the Saturn encounter, we had moved this platform too much, too fast, and that if we used the platform in a consistently at a slower rate, and if we constrained the total amount of angular motion that we applied to the platform, then in fact we would be in a pretty safe condition.
Voyager 2, the amazing robot spacecraft that was launched 8.5 years ago and just kept on going, passed yet another milestone today as it became the first spacecraft to fly past the planet Uranus.
Uranus is not a very photogenic place. It looks more or less like a big blue ping pong ball. But we did see clouds in the atmosphere of Uranus, and they did tell us something. In fact, Uranus is a tipped-over version of Jupiter and Saturn. The cloud patterns are more muted, but they have the same kind of banded structure that Jupiter and Saturn have. Now, what that says is that the spin of a planet is the all-important process or thing that organizes weather.
Uranus is a very peculiar planet in the sense it's tipped on its side right now with the south polar region pointed at the sun. We had expected that the magnetic field pole would also be up near the rotational axis, so the magnetic field would be tipped on its side. What we found was, to everyone's surprise, that the magnetic field, rather than being pointed at the sun, was tilted some 60 degrees from the rotation axis. Not only that, but the center of the magnetic field was displaced from the center of the planet by almost a third of the radius of the planet. Uranus's magnetic field is a bit stronger than that on Saturn, and it extends some 300,000 miles from the planet. The rotation period, that is the length of the day on Uranus, is measured by how rapidly the magnetic field is rotating, is about 17.25 hours.
The big problem going on to Uranus is that it's twice as far away from the Earth as Saturn is. In order to compensate for the darker environment, we had to make sure that the spacecraft would be steadier. And to make the spacecraft steadier, we had to deal with the things that made the spacecraft move while it was just flying through space.
The Uranian rings are inherently dark. In fact, they are no brighter than coal dust. So imagine trying to take an image of coal dust at twilight, but it's even worse than that. So we had to worry about the necessity of using long exposures and the fact that the spacecraft scan platform is not a stable platform and always moves someone. Best image that we got, in fact, of the Uranian ring system, we had to use image motion compensation. What we saw in that image is a sheet of dust that extends throughout the Uranian ring system, and this sheet of dust is punctuated by features, many of them. There are more features in that picture than there are rings seen from inbound. So we have 9 narrow rings seen in the inbound images, and one newly discovered one, the Lambda ring.
As a matter of fact, if we had our choice, we never would have gone close to Miranda. In order to get to Neptune, we were obliged to go a particular distance from Uranus in order to get the right gravitational deflection on the spacecraft. Well, it turned out that that distance was exactly the distance that Miranda's orbit is from Uranus. It is a very exotic and complicated place. Most of the regions that we viewed are heavily cratered, old, rolling, ancient terrains. But embedded in these are very unusual circular patches, almost like racetracks, of groove terrains that run around in circular bands surrounding very complicated crisscrossing structures in the interiors.
We addressed the question, what can we do to hear the data better? We did come up with a technique called arraying, where we took existing antennas and electronically wired them together so that in fact it had the appearance of being one larger antenna. And we did that in Australia, the primary receiving site at Uranus, and combined the DSN's stations with a bowed antenna from the Australian radio astronomy community at Parkes.
Radio sign, Parkes.
Stand by, Parkes.
While we were moving from Uranus to Neptune on the ground, we had 2 major things to do. First of all, we reprogrammed the software on board the spacecraft to do 2 things: to stabilize the spacecraft so that the pictures would not be smeared, and to add some new techniques to the spacecraft that would allow it to pan and track the planet when we were taking pictures near the planet. Second thing we had to do was improve the communications capability. We did that since Neptune is twice as far away from a communication standpoint as Uranus. We did that by enlarging the size of the antennas on the Earth and by adding several new sets of antennas into our deep space network to help compensate for the distance.
It is mission accomplished for Voyager 2. The space probe is headed out of the solar system tonight after photographing parts of the universe no one had ever seen before.
Now, we had some hints from Earth-based observations that Neptune had a few clouds, and at least that was better than Uranus. But we really weren't prepared for the spectacular weather activity that Voyager found. In fact, Neptune is the windiest planet in the solar system, and I was totally unprepared for that. The winds are 325 meters per second. That's the speed that the great dark spot is moving relative to the inside of Neptune. Everything's going to the east, but the great dark spot is going more slowly to the east than the inside of Neptune.
We had expected, because Neptune is not tipped on its side as a planet, but is an upright planet, that the magnetic field axis would be aligned with the rotation axis. That is, the poles would be near the rotational pole. We were surprised again. The magnetic field is tilted by 47 degrees in the case of Neptune, and its center of the magnetic field is offset by almost 2/3 of the radius of the planet. Its magnetic field is somewhat weaker, only about half of that of Saturn's, for instance, at the surface, and its magnetic field extends only about 400,000 miles from its surface. We did discover that the rotation period of the magnetic field is about 16 hours and 7 minutes, faster than Uranus, but slower than both Jupiter and Saturn.
Systems Etiquette Control. Yes, sir. I'd like to report that the scan platform is in the proper position as expected.
As we approached Neptune, we were approaching with the sun and the Earth almost directly behind us, so you could see virtually a full disk of Neptune. And we aimed to go right over the North Pole, right up over the top of Neptune, very, very close to Neptune. The trajectory was then bent by gravity, moved south, and we intercepted Triton while it was behind Neptune and underneath it.
Well, as we got closer and closer to Triton, it got smaller and smaller and smaller, and at the same time brighter and brighter. It turned out to be the brightest thing we've seen in the solar system. North of the polar cap, in the north, just above the equator, we find one thing we call the cantaloupe terrain. It has a system of crisscrossing ridges which produce a set of almost squarish to ovoid dimples throughout the surface. Now we're talking about a surface which is 37 degrees above absolute zero. This is the coldest thing in the solar system by far. Even the cold atmospheres of things like Neptune are warmer. It was unthinkable to find activity going on a planet whose surface temperature is that low. I mean, this is getting down to the point where molecules stop. It was about a month after the Voyager encounter that we were looking at stereo images way down in the southernmost part of Triton's polar cap, and we saw most of the features lined up as if they were on a perfect sphere. In fact, the two best examples turn out to be active eruptions in which material is being blown from the surface in a vertical column to an altitude of 8 kilometers, roughly 5 miles. Voyager discovered 6 new moons at Neptune. 2 of them were found in the ring arc or ring system, orbiting along 2 of the ring arcs. So apparently shepherding the edges of those ring arcs in some way.
When we look at Neptune's ring system, as we can see here in this mosaic, we see 3 continuous rings quite easily. There is an outer ring. It's the ring in which, in fact, the 3 arcs are embedded. There's an inner ring which, in high phase geometry, appears brighter than the outer ring. That tells us right away it's dustier than the outer ring. And then we see an inner, more diffuse ring at something like 42,000 kilometers from the center of the planet.
We believe now that we'll be able to communicate with Voyager essentially as long as it stays alive. 2 things will probably stop its life. First of all, it has a power source on board, which is a small nuclear power source called radioisotope thermal generators. And they operate by the radioactive decay of plutonium, which generates heat, which in turn is converted into electricity. In about 20 to 25 years, we expect to be low enough so that there's not enough power to keep the critical subsystems of the spacecraft operating. Or, at about the same time, we could possibly run out of attitude control fuel. That's the fuel which goes through little thrusters, which keeps the spacecraft stabilized and pointed at the Earth.
Now, between the stars, there's a dilute gas, ionized gas, filling interstellar space. It's called the interstellar medium. Each star blows a bubble in that interstellar gas. Our own sun does that. That bubble, in the case of our sun, is called the heliosphere. We don't know how large that bubble is. It may be that the distance to the edge of the bubble, called the heliopause, is 100 times the distance from the Earth to the sun. That is 3 times further than it is out to Neptune. In which case, 25 years, Voyager 1, which will at that point be 130 times as far from the sun as the Earth, could well be returning data from interstellar space for the first time. There will be a part of Earth which will roam essentially forever in the galaxy, and that will be the Voyager spacecraft.